Hey everyone, welcome to The Explainer. Today we're jumping straight into an absolutely fascinating journey through the biology of human sensation. We're looking at a bizarre medical mystery that's honestly baffled doctors for centuries, and we'll see how finally cracking this case is leading us right to the future of non-addictive medicine. Let's get into it.
So I want you to take a second and just imagine a life completely without physical pain. Like never feeling the sting of a paper cut or the agonizing throb of a broken bone or, that sharp shock when you accidentally touch a hot stove. On the surface, man, that sounds like a superpower, right? Total invincibility. But as we're about to see, living completely free of pain actually hides a really dark and incredibly dangerous paradox.
Okay, let's dive into this. The reality of a painless life is actually pretty horrifying. What we're looking at here is the result of congenital insensitivity to pain, or CIP for short. Because individuals with CIP literally cannot feel discomfort, they suffer from severe, frequent, and totally unnoticed injuries. We're talking about kids who might chew on their own fingers, bite their lips until severe ulcers form, or even walk around on fractured legs without so much as a flinch. No way, right? But without pain screaming at them to stop, these minor accidents snowball into massive, disfiguring, and even life-threatening physical traumas.
And what makes CIP so fascinating and devastating, honestly, is that it's not a total loss of sensation. It's not like being completely numb. People with CIP can still feel the light touch on their skin. They know exactly where their limbs are in space. Heck, they could often even sense changes in temperature. But that critical warning system, the body's built-in alarm bells of pain, is just silenced. Because they don't feel the burning heat, they get severe thermal burns. Because they don't feel a cut, wounds get infected and spread completely unnoticed. So it turns out, pain isn't just some annoying glitch in our biology. It's our absolute most crucial defense mechanism.
To really understand CIP, we kind of need to look at the baseline biology here. In a normal system, when tissue damage happens, these specialized sensors called nociceptors fire off. From there, electrical impulses literally travel along the body's white matter superhighways, carrying that signal straight up the spinal cord and right into the brain's cortex for processing. And this is the exact moment your brain actually gets the message and decides, okay, what do we do about this?
Once that signal hits the brain, this beautifully complex, integrated response takes over. First off, your salience network lights up, essentially screaming, hey, pay attention to this right now. Then, your motor pathways kick into gear, automatically forcing you to yank your hand away from whatever's hurting you. And finally, modulation networks flood your system with chemicals like endorphins to help you cope with the shock. But here's the wild part. While we all share this exact same basic wiring, individual sensitivity varies wildly. It's exactly why one person might get this euphoric runner's high from exercise, while someone else might suffer from agonizing, untreatable chronic pain from a seemingly minor injury.
Now, for a really long time, cases of CIP completely baffled the medical world. The very first descriptions of these painless, self-injuring patients popped up back in the 19th century, and doctors were just thoroughly confused. By the 1950s, scientists started noticing family patterns and figured out, okay, this is an inherited genetic disorder. But it wasn't until 1994 that we had a massive game-changing breakthrough. Researchers finally tracked the condition down to a single genetic culprit, the SCN9A gene.
So what does this gene actually do? The SCN9A gene controls the production of a very specific protein structure. It's a voltage-gated sodium channel called NaV1.7. Try to picture these channels as microscopic toll booths sitting right on the surface of your nerve cells. When something painful happens, these toll booths swing open, allowing sodium ions to just rush into the cell. This sudden rush creates the electrical action potential, basically the spark that allows the pain signal to fire and travel all the way up that superhighway to your brain.
And once scientists understood this toll booth mechanism, everything just clicked into place. They realized that in people with CIP, a genetic glitch causes a loss of function mutation. Basically, their NaV1.7 toll booths are permanently locked shut. The pain sensors are there, but the signal literally cannot fire. On the flip side, if someone has a gain of function mutation, their toll booths are thrown wide open, firing non-stop. This throws the whole system into overdrive, causing horrifying inherited chronic pain syndromes, where patients feel intense, burning pain without any actual physical injury.
Well, this genetic discovery threw open a massive door in pharmacology. Think about it. If a locked NaV1.7 toll booth naturally makes it impossible to feel pain, could we create a drug that intentionally does exactly that? If we could temporarily mimic that CIP glitch, we could theoretically stop pain at the source, right at the peripheral nerves, long before the signal ever even reaches the brain. This is, without a doubt, the holy grail of pain medicine, a way to stop chronic pain dead in its tracks without relying on highly addictive opioids. But, as you might guess, translating this awesome genetic proof into a drug you can actually take has been incredibly frustrating. Major pharmaceutical companies jumped all over this, but compounds like Pfizer's highly anticipated NaV1.7 inhibitor completely failed to beat a standard placebo in clinical trials for diabetic nerve pain. So why? Well, it turns out these drugs struggled to bind perfectly to the human target. And even wilder, recent studies found that people with natural CIP actually rely on central opioid pathways in their brain to stay pain-free. That means simply blocking NaV1.7 in your outer nerves isn't enough to kill the pain without some level of opioid synergy humming in the background. Because of those immense hurdles, researchers made a really clever strategic pivot to a close cousin of that channel, the NaV1.8 sodium channel. Now, what's really interesting here is that while NaV1.7 is tied up with those central brain opioid pathways, NaV1.8 operates almost entirely out in the peripheral nervous system. It basically acts as a volume dial for the pain signal in your outer nerves, completely bypassing the central nervous system. This means that if we target NaV1.8, we could potentially avoid central side effects like addiction and dizziness entirely.
This shift has kicked off a cutting-edge race to develop selective NaV1.8 blockers. Vertex Pharmaceuticals led the charge with a drug called VX150, and more recently, they've been testing a highly anticipated compound named VX548. This is designed to target moderate to severe acute pain, and the goal is huge: drastically reduce our reliance on traditional painkillers. Now, yeah, there have been some recent clinical bumps in the road, like some mixed data in trials for sciatica, but VX548 is still showing incredible promise in acute settings. We are looking at a massive frontier in finally avoiding the dependency issues that have plagued pain management for decades.
And this whole journey brilliantly illustrates where medicine is heading. As the quote says, figuring out how your brain responds to pain is the key to finding the best treatment for you. By mapping out these individual pathways, from your specific NaV1.7 and NaV1.8 channels down to exactly how your brain's white matter lights up, we are finally moving away from the old one-size-fits-all approach. We're entering a totally new era of highly customized pain relief, tailored literally to the exact biological makeup of your own nervous system.
As we wrap up this explainer, I want to leave you with a thought to chew on. How will understanding our absolute rarest genetic anomalies unlock the everyday miracles of tomorrow? It is honestly so humbling to realize that the terrifying mystery of CINP, a disorder that completely robs people of their biological alarm system, has actually handed us the blueprint to the human nervous system. By studying those who tragically cannot feel pain at all, we are paving the way to cure chronic, debilitating suffering for millions of people worldwide. Thank you so much for joining me on this deep dive, and as always, keep asking the big questions.